man, he's the myth, he's the legend, he's the scientist with all the answers to all the questions. It's time for another episode of Alex's Science Corner.
That was a nice try there. I don't know if we have to go back to anything else.
All right. What's going on in the wide world of science, Alex?
Not much. It's been pretty quiet. You see anything interesting, Brian?
All right. Thanks a lot. We'll be back next week. If you have any questions about these stories or anything else science-related, feel free to call.
No, there's some big news this past week. There's a image of a black hole. We got an image of a black hole. Oh my God, we got an image of a black hole. Yeah, it's cool. I know it looks like a coffee stain.
Isn't that a big deal, though? It's a big deal.
It's a big deal.
Right.
It's hundreds of astronomers, thousands of technicians from astronomy sites around the world work together to get this one picture, and it's a big deal.
I thought it was, yeah.
Yeah.
If you're wondering what we're talking about, by the way, I did post the picture on the Saturday Morning Club Facebook page.
Right,
if you want to check it out.
And any news site you go to probably has a picture of it too. And I know it looks like a coffee stain on a nice table.
But still, it's amazing that they've captured this image at all.
I mean, to give a scale, think about taking a picture. You're standing in the middle of Danbury, trying to take a picture of a grain of sand in the middle of Brewster from Danbury. That's what kind of thing they're trying to do here, okay? Let's talk about the black hole first, because there's two fascinating parts about this. The black hole that we took a picture of is the supermassive black hole in the center of galaxy M87. This is 5 million light years away. The black hole itself is massive. Now, the black hole that's in the center of our galaxy is only 4 million solar masses. It's only the weight of 4 million of our star, okay? The black hole that's in the center of the M87 is 6.5 billion solar masses. It's big. Our black hole is only about as big as Earth's orbit around the sun. This black hole is bigger than our solar system. It's bigger than how far Pluto is from the sun.
Wow.
Okay. It's huge. This is one of the reasons why, as far away as it was easier for them to take a picture of an M87 than the black hole in the center of our galaxy. Because even though that other black hole is a lot closer, we have to look through a lot more dust, a lot more material. They did take a picture of our black hole in the center of our galaxy, but it's not a good picture. The other thing, too, is our black hole is not feeding, and because it's smaller, it's only as big as our orbit around the sun. The material that's spinning around it is going a lot faster, and so as they're taking the picture, it's going to look fuzzier, like a motion blur on a camera. The other black hole is so big that even though the material around it is spinning near the speed of light, it is still so large that it's not going to change enough during the time that they took the picture.
Now, the picture itself, it looks like the edge of it, the hole, is actually on fire.
Right, and what we're looking at there, the center part of that image is known as the shadow of the black hole, and I'll explain that in a minute. But the outer ring is the material, the accretion disk, the material that is slowly spiraling in or not yet spiraling in, and it's a material in orbit around it. Just like Saturn's rings are orbiting around Saturn, this is material that's orbiting around the black hole. And because it's going so fast, it's generating heat, and that heat is being seen in radio waves.
So it's spontaneously combusting because
it's not spontaneously combusting, it's just hot because of how fast
it's moving so fast that it's igniting.
It's not igniting,
no?
It's hot.
It's
just like if you put a rock into a fire and you take it out, the rock is hot. Okay, so it's like the material around there is hot. But it's radiating out in radio waves, and that's the image that we're seeing is the radio waves coming off of that disk. Now, the interesting thing about it is because of the way light shapes around the black hole itself, the center black area that you're seeing on that image, Only the center 1/3 is the actual black hole. The rest of it is a shadow, and it's really hard to describe because of the way the light bends around it. But in a strange way, that outer part, before you get to the colored portion, you're seeing the back of the black hole in the outer parts of that shadow. That's why they're calling it the shadow. Because if it could have emitted light, that light would be coming around and you'd see the back of the black hole.
What's on the other side?
I mean on the other side of the black hole itself?
Yeah.
Are you talking about inside of the event
What
horizon?
happens when stuff goes through it? I mean, where does it go?
Into the black hole.
No one knows what
Well,
happens.
I mean, it's good. Once it crosses the event horizon, that's where our math breaks down.
So we have no idea what happens afterwards.
We know a bunch of stuff, but we just don't know much more because the math just breaks down at that
But
point.
inevitably, anything going through there is destroyed.
Well, there's a lot of theories about that, and that's going to be above today's lesson for Alex's Science Corner. But it's we're not. There's a thing called black hole evaporation, which I'll another time. But that ring around it, like I said, is the material, and it's glowing material.
Right.
The center
which
section,
is very obvious in the photo if you check it out.
And the center section, the center 1/3 is the black hole itself, and what you have between that the outer 2/3 of that dark area is the shadow, and that is looking at various aspects of the back of the black hole.
Okay.
We're not seeing anything, but that's what that is. Huge object.
This thing is capable of sucking in a planet.
Oh, planet nothing. I mean, we're talking about
like solar systems that can pull it.
It is holding that galaxy together. The supermassive black holes in the center of galaxies, everything is orbiting around that galaxy. When you see spiral galaxies, they have a supermassive black hole in the center of them. And that's what the whole galaxy is orbiting around.
Do you think it's possible that to go through, you'd end up in another galaxy?
Incredibly unlikely.
No?
You'd be ripped apart before you got there.
Okay.
That's what the accretion disk is. It's dust and material of things that have been ripped to pieces.
So there's probably no survival going through
No.
that.
No. And then the thing is, once you pass the event horizon, our math breaks down at that point. And that's where we have problems. We can go a little bit ways in, like where the light orbits around inside of the event horizon, but can't go out.
There's no way a probe could ever survive going through something like that.
Nothing that we've ever thought about. Yeah.
Okay.
But the second part of the story is what effort it took to get this picture. To take this picture, they had to get 8 radio telescopes around the world. 2 in the United States, 2 in South America, 2 in Europe. Actually, there's like 3, another 1 or 2 in Hawaii, and a radio telescope at the South Pole. They all had to be looking at the same time, all had to have clear weather. It took 4 days of them to image this black hole. The reason why they had the telescope spread out across the Earth is because to get enough fine detail, you had to have a radio telescope as big as the Earth. So what they did is using super, super accurate clocks. They took the radio telescopes and they would all look at the same spot, and then they took the data from each of these telescopes, and there's 1 petabyte of data from each of these telescopes. And for people who are wondering, that a petabyte is 1,000 terabytes. So think of your standard good computer nowadays that will have a 1 terabyte hard drive in it. The data storage for 1,000 computers for each of these radio telescopes. There's so much data you can't transmit over the internet. It is faster and cheaper to pack all that stuff, fly it overnight to the processing center in hard drives than it is to try and transmit over the internet. It's so much faster that way that they had to wait until summertime in the South Pole to pack up all those hard drives that are generated from the South Pole radio telescope. So they had to wait 6 months, and that was still faster than if they tried to transmit that over the internet.
Wow.
Massive amount of data. They then had to take it to processing centers where they took all of this data and started to match up the data and deal with stuff like noise from the radio telescopes, intermittent noise that's coming in from other sources, so they could pull out the signal of the black hole from everything else that the radio telescope picked up. That took months of work to get all this data together, get it all matched up, get it picked up. They separated out the work to 4 separate teams that all worked independently. The reason is if they all came up with the same result, they've got the image. If, 1 or 2 or 3, or if they started to look different, it's back to the drawing board and try and pick that stuff up out again. So they had 4 different teams going over these data sets, independently processing the data. 200 astronomers and teams around the world were doing this. You had thousands of technicians, of physicists, of computer specialists doing all that work to get this all put together. It's just an amazing worldwide project.
Now, who was the scientist, this young scientist that they were lauding for this? There was I don't know who she was.
Katie Bowman.
Okay.
She's one of the computer specialists. When this project started about 4 years ago, she was a graduate student. She is now a professor at California Institute of Technology. She did a TEDx talk 3 years ago talking about the work that was involved before they actually started taking the measurements, the work that was being done on the computer side to generate the software and the algorithms to figure all the stuff up and match all the data together so that they could pull the image out of the data. She was one of the people that led one of the teams that did that work.
She's 29 years old.
Yeah, she looks like a high school kid. It's like getting ready to send out her resume. She's a doctor.
Very smart lady.
Yeah.
Wow. So if you haven't seen this photo, you should. And it is posted.
And again, it doesn't look like much, but the work, what it represents.
It's pretty cool. I think you should. You can easily Google it. It'll pop up, or you go to the Saturday Morning Club Facebook page. It's posted there.
Yeah, and I also, previous on the Alex's Science Corner, there's another video I posted about this person who's talking about what you expect to see from the image.
Okay.
So, but yeah, so anyway, that happened.
Yeah, pretty exciting stuff. Very exciting. We're going to have to move along here.
Mm-hmm.
But if you have any questions about this story, Alex would be more than happy to discuss them with you right now. Feel free to call us at 203-837-9924.